Hey guys, and welcome to another fun day of Music with Mr. T. Today we're going to be talking a little bit about music and science and sound. Looking at our standard documents, we're looking at 4.P.4b. Sound as a form of energy is produced by vibrating objects and has specific properties including pitch and volume. Sound travels through the air and other materials and is used to communicate information in various forms of technology. So as we go through this lesson, you're going to be able to conduct a scientific experiment to see how different things that make sounds affect the pitch and volume using one of our online apps. And you're also going to be able to use that app to analyze and interpret your data and the information that the computer readout gives you. So we're going to look at some things from a number of websites, as well as show you how to access our sound analyzer website on Google. And I hope that you have a fun time learning a little bit about the science of sound and how we can connect music and science together. Here we go. Welcome to dkfindout.com, where it's going to help us explore and learn a little bit about pitch and wavelength of sound. So, as we see here on the left, the sound of an object makes changes depending on how fast it's vibrating. When an object vibrates quickly, high-pitched sounds are heard. Low-pitched sounds come from things that vibrate more slowly. We'll see that when we take a look at some of our other instruments, also with a spectrograph through Google Chrome Music Lab. Humans can hear sounds of different pitches, but there are sounds that they cannot hear. Human ears cannot detect very low-pitched noises, known as infrasound, or high-pitched noises called ultrasound. So when we make sounds, there's things that are called wavelengths. The higher sound, the faster vibration, has a shorter wavelength. Let me get out of the way here. So here's a high-pitched sound. Or not. And looking here at a medium wavelength. This is a medium pitched sound. The wavelength's a little bit bigger, a little bit longer. And then the low sound here is a low pitch, and the wavelength is the longest. So how are sounds created? Sounds are created when something vibrates or shakes back and forth, sending waves of vibrations into the ears of the listeners. When a bell is struck, the metal vibrates. The vibrations travel through the air as sound waves. When these waves reach our ears, they make our eardrums vibrate, and we hear the sound of the bell ringing. Sound always needs to travel through some sort of medium, such as air, water, or metal. In a vacuum, where there is no air, sound waves do not have anything to travel through, and the bell would not be heard. So take a look at this drum. When these wooden sticks hit the drum skin vibrates to produce sound. The waves travel in the direction of the ear to where they're heard. Some of these waves over here are getting compressed, and some of them are experiencing what's called rarefaction. Compression are parts of a sound wave where the particles of the medium through which the sound travels and are squeezed together. Compression, squeezing them together. And rarefactions are parts of the sound wave where the particles of the medium through which the sounds are stretched apart or traveled. Loudness, also known as dynamics in music, is what we're talking about next. Sound travels as waves of vibrations. The bigger the waves, the more energy they carry, and the louder the sound. When they arrive at your ears, louder sounds push harder against your eardrums. From something like rustling leaves to jet engines, the human ear can detect an amazing range of loud and quiet sounds. So the thing that we're going to look at with talking about loudness of sound is something called amplitude. Scientists often draw waves as wavy lines like these. The taller the wave in the graph, the louder the sound, and the height is called the amplitude. So if you walk outside and play in rustling leaves, you will notice that there is a very low amplitude. This is a very short height. If we say get on the interstate I-26 or 526 and we're hearing all the traffic, We say that's a higher amplitude because here the height is higher, therefore we have a louder sound. And of course, a rocket launching from the space station or from where it's launching is a very loud sound, and it's going to have a very tall wave and a very high amplitude. Here are our tone blocks. Let's take a look at the spectrogram. Here is the flute in our Google Music Chrome Lab spectrograph. Now a harp. Notice those red peaks are lower when the pitches get lower. Here is a whistle. Higher sounds, higher peaks. A trombone. A drum machine. A bird. Notice the high sounds up here. And one more, a dial-up modem. Let's go back to the microphone. Here's me talking, and you notice that as I talk, I have a lot of specs or spectrographs in the low and high. If I speak down here, it's going down low. If I speak up here, my pitches are going up and down, up and down. So now let's go over to our piano. Let's start with middle C and see what we get on our spectrogram. Let's go to a higher C and the highest C and a low C. So we see that big red peak there and a lower C. Lots of vibration in the low half there. Now let's see what the spectrograph looks like when I play a song. Lots of mids and lows there. Let's see if I play that same song higher if our spectrograph changes. So it gets lighter. And if we go lower. Here is my djembe. My djembe is my percussion instrument, an African percussion instrument. Let's start with some rims. Okay, let's see some tones. And a few basses. I'm going to play that pattern again, and I want you to watch and notice how things are changing as we play the pattern. Here we go. Notice those big beats at the bottom where the big bass hits, right there at the bottom. And then when I had the slaps on the rims, it was a little bit lighter. All right, let's take a look at a couple of more instruments for our spectrograph. Let's start the microphone back up. There we go. First, we have some jingle bell wrist bells. You see they're noticing the higher sounds of those. We have a recorder. And a gourd shake array. All right, so now that our lesson is over, I want to highlight for you how to access Chrome Music Lab and to get to the spectrograph so that you can try and make your own sounds as well. So once you open Google Chrome, search Chrome Music Lab right here, and you'll click the first link that comes up. And then once that loads, go over to the fourth box on the top row and click Spectrogram. Then from here, just like we have done, you can use the microphone for it to analyze sounds that you create, or you can select the finger, which allows you to draw your own sound. As well as all of the other ones we've demonstrated today. I hope you enjoy it. Thanks so much for coming by and watching today, and I can't wait to teach you more about the science of sound.